In this video session, we will see the overview of virtual memory, what is a virtual memory, and what are the advantages of a virtual memory. In this diagram, we can see that we have a physical RAM of say up to 1 GB. The CPU executes the instruction from the physical RAM, and on a multiprocessing operating system such as Linux, we have several processes running, and if each process needs to access more addressing space than the available physical RAM, then this is achieved using the concept of virtual memory. So, virtual memory is a concept in which each process is given more addressing space than the available physical RAM. The advantages of virtual memory is each process can have a private memory in which it can have a data protection, and the data can be protected from other process. In the next video session, we will see how the virtual memory is being managed.
Hello and welcome. In this video session, we are going to discuss the virtual memory management and the page table of a process. The topic virtual memory and memory management in general is a very important topic in Linux system programming. Many modern kernels has a concept of virtual memory, and Linux also has similar techniques in which it can efficiently handle the CPU and the RAM. RAM is also called as the physical memory. The physical memory is the place where instructions fetched from secondary memory like hard disk is stored, and the CPU can access the instructions from the physical memory. The physical memory is limited in size and there are many processes running. Hence, the virtual memory concept arrives. Let's understand the concept of virtual memory. Let's assume we have a RAM of 1 GB and we have say 4 processes running. Each process has a memory space of 4 GB. Now, if all 4 processes has to run in memory, then physical memory should be 4 cross 4, that is 16 GB in total. Now, assume 10 process running in physical memory. In this case, the total physical memory size would be 10 into 4, that is 40 GB. Hence, to run 10 process of 4 GB each, we need physical memory of 40 GB. But practically, we cannot have such a huge size of RAM. Hence, the concept of virtual memory arises, where we store only few parts of process memory in RAM and remaining process memory is stored in secondary memory. And on need basis, the process memory is loaded to RAM. So all this is done by the swapper process in background, and user gets a feeling that all 4 GB process memory is running in RAM. Now in virtual memory, each process has its own memory space. On a 32-bit system, the address space can map up to 4 GB, that is 2 raised to power 32. Each process can have its own memory space of 4 GB. Each process has a private memory space. This means memory of one process cannot be directly accessed by other process. And the same way, each process maintains its private data. As we have discussed in previous video sessions, there are different memory segments of a process like text segment, initialized and uninitialized data segment, stack segment, and the heap segment. Usually on a 4 GB memory space, the first 3 GB is a user space and the top 1 GB is the kernel space. Let's see this using a diagram. This diagram shows the virtual memory of a process. This memory space is from 0x 0000 0000 to 0x FFFF FFFF. That means 4 GB memory space. But in reality, each process cannot have all 4 GB memory in physical memory or RAM, also called as main memory. Only few parts of process memory is present on RAM. This is the concept of virtual memory, where even though the physical memory or RAM cannot hold full 4 GB process memory of all running process, only some part of process memory is loaded in RAM and remaining process memory is swapped in or swapped out between main memory or RAM and secondary memory. Now, the kernel has top 1 GB. So, the address from 0x C000 to 0x FFFF is 1 GB. This 1 GB is the kernel space and remaining lower 3 GB is user space. In the 3 GB user space, we have start of stack. As the program executes, each function has its own stack frame. So here, the main function has a stack frame, and when main calls some other function, the stack frame of that function is occupied onto the stack, and the top of the stack is called a stack pointer, and it always points to the top of the stack. Now, at some point, when this function returns back to the calling function, this top stack frame is deleted, and now the stack pointer points to this point, which is nothing but the stack frame of calling function. Also, there is a heap memory. This address can be considered as a start of heap, and the heap grows upwards whereas stack grows downwards. So, stack grows downwards towards lower address memory from upper address memory, and heap grows from lower address memory to higher address memory. Here, from this point to this point, there is some heap memory that has been allocated during dynamic memory allocation, and the space between stack and the heap is unallocated memory, and this memory is being used by both stack as well as the heap. But the user program should make sure that the stack does not cross over the heap, and if it crosses, stack overflow occurs. Then we have the data segment. From this point to here, we have the initialized data segment. Then from here to here, we have uninitialized data segment. And from this point, from here to here, we have text segment or program segment. Now, let's discuss the concept of page frame. A virtual memory of each process can be split into small fixed size unit called as the pages. Usually, a page by default is 4 KB, but this page size can be configurable to different sizes. Now, we have this process memory, which is divided into fixed memory size called as frames. And we have similarly the physical memory, which is also divided in series of page frames. This means the page frame size is constant for both process and the physical memory. At any given point of time, only few pages of a process can be present in the physical memory. Each process page memory has a ID starting from 0, and the pages which are present in physical memory is entered in the table called page table. Kernel maintains a page table for every process, and the page which are present on the physical memory are called as resident sets. The copies of unused pages whose entry is not present in the page table of a process are maintained in swap area. We will see more on page table in next slide. Usually a disk is used for a swap area, and the memory keeps swapping between the main memory and the swap memory based on the scheduling algorithm. So now, as we have discussed, the page frame is a configurable parameter, and it generally vary from 4 KB or 8 KB or 16 KB. In Linux, the default page frame size is 4 KB. Now let's see what is a page table. In this figure, we can see some important concepts. In the center of the diagram, we have physical memory, which is the RAM, and this RAM is divided into page frames or of fixed memory, say 4 kilobyte. So page frame 0 is 4 kilobyte, page frame 1 is 4 kilobyte. Now on the right hand side and the left hand side, we see process A and process B. So this process A has completely 4 GB of virtual memory space, and process B also has 4 GB of virtual memory space. But here we have shown a small pot of memory. In this case, we have taken page 0, 1, 2, 3 and 4 for process A, and page 0, 1, 2 for process B. We have a fixed frame size of 4 KB, both in process as well as the physical memory, and this represents the swap memory, or usually the hard disk or the secondary memory where the swap in and swap out occurs. Now, there is a page table maintained by kernel for every process. The main intention of the page table is to specify which page of a given process is loaded onto the physical memory and where it is loaded in physical memory. As, as we have discussed earlier, a process has different page frames, and few page frames are loaded onto the physical memory, and not all page frames are loaded onto the physical memory. In this case, we have page 0 is loaded onto page frame 3. So this page 0 of process A is completely present in page 3 of physical RAM. Page 1 is loaded onto page 4 of physical RAM. Page 2 of process A is loaded onto page 5 of main memory or physical memory. And page 3 is loaded onto 0th page location of RAM. At this given point of time, page number 0, 1, 2, 3 of process A are loaded in RAM. As we can see, there is no entry for process A's page 4 in page table. This means this page memory is not present in the physical memory, and it is stored in swap area or secondary memory. Similarly, process B, we can take 3 pages as an example here: page 0, page 1 and page 2. Page 0th entry is present in the page table of process B, and page 0 of process B is loaded onto page 1 of physical RAM, and page 1 of process B is loaded onto page 2 of physical RAM, and page 2 of process B is loaded on page 6 of physical RAM. Now, this is the page table, and page table is applicable per process as discussed. So each process has a page table entry where it has entry of the pages of the process that are loaded onto the physical memory. So now in this case, the page 4 of process B is not present in page table. This means process B's page 4 is present on swap memory. Now let's see what is a page fault. Page fault occurs when a process tries to access a page that is not currently present in the physical memory. A page fault occurs. Let's see this with an example. Let's say process A process A's instruction, which is present in process A's page 4, is to be executed by CPU. The kernel first checks if page 4 is already present in RAM by checking the process A's page table entry. If page 4 is not present in its page table, a page fault occurs and the process execution is suspended and the page 4 is loaded from the swap area to the main memory. And once it is loaded onto the main memory, a entry of this page is made in the page table of process A. So in this video session, we have learned the virtual memory of a process. In next video session, let's discuss command line argument of a process. Thank you. Hello and welcome. In this video session, let's discuss the command line argument of a process. In the main function, we have two parameters, which is argc and argv. We call this as the command line argument. Argc is of integer type and argv is an array of pointers to string. Before explaining this program, let's execute this and see what is the output of this program. We have the name of this program as cli1.c. Let's compile the program. Now we have got the output file as cli1. Let's pass string. This is a command line demo as a parameter to this exe file. In previous examples, we were just running the program, but now we are giving some extra parameter to the exe file. Let's execute this file. Here, if we see the value of argc is 7, this is nothing but the total number of strings present when we execute the program. That is, the first string is ./cli1 followed by second string, third string, fourth, fifth, sixth and seventh string. So in total, we have 7 strings and now we are printing all the strings in a loop using argc and argv. Here argv of 0 points to this first string, argv of 1 points to this second string, argv of 2 points to this string and so on. Now let's see one more example. This is just to demonstrate a small use case. So one more point to consider here is the command line argument are stored as part of stack of the main program. So this forms the stack frame of the main program. In this case, we are trying to have a small use case and we are trying to add two numbers or subtract two numbers based on user's input. If user specifies add, then the following two numbers are added. If user specifies a sub, then the following two numbers are subtracted. Let's compile this program and see the output. Let's run the program. Now here we give add as one of the parameters. Then let's pass 8 and 3 as following parameters. In this case, when we run, we have got argc equal to 4. So there are total 4 parameters and argv points to the individual strings. That is, argv of 0 points to first string, argv of 1 points to the second string and so on. So now let's see the output, then understand the program. Here we see addition results equal to 11. That is 8 plus 3 is 11. Here each parameter that we pass is a string. So here we check whether user has provided add or sub as command line argument. And if it is add, then we add the next two parameters. that is argv of 2 and argv of 3. If you notice here, the command line parameters are strings. We are going to convert from ASCII to integer for both the parameter before performing addition or subtraction of these variables. Let's run the same program once again and let's pass sub as command line argument and let's see the output. Here, the given string is converted into numbers and subtraction is performed. So, when this program is executed, a new process is forked or created, and this command line argument forms the part of the stack frame of the main function. In next video session, we will discuss environment of a process. Thank you. Hello and welcome. In this video session, let's discuss the environment of a process. Each process has a set or a list of strings called as environment. Each of these strings are in form of name and value pairs. Thus, the environment represents a set of name value pairs that can be used to hold information. The name in the list are referred to as environment variables. So, this is called as a environment variable. Let's see an example of this to understand the environment of a process. This is a small program to list the environment of the process. Here we have a global variable environ which holds all the list of environment that is used in the process. We loop through each of the list and print the environment. Let's run this program to understand the environment of a process. So let's compile the program and create output file called env1. Now let's run the output file. So when we run this program, the program will execute as a process and all the environment variable of this process is listed in this program. Let's execute program to understand the output. Once we run the program, we can see that we have environment variables. This is the environment variables and this corresponds to the name value pair. We can see the list of environment variables and corresponding value assigned to the environment variables. So these are the different environment variables of a process, and these environment variables are visible across the function within the process. This means every function called within this process can access this environment variables, and this environment variables acts as a global variables. Whereas in the previous session, we saw a command line argument where the command line arguments are limited only to the main function and the command line arguments are not visible outside the main function. So this is one of the advantage of using environment variables where we can share the information across the functions within the process. Now let's see one more example of environment variables. In this case, let's see how to use getenv. We have the list of environment variables. In order to get the value of this environment variables, we use getenv. Here we have to pass the environment variable that we need to get the value of, and it returns the value of that environment variable. So in this case, when we say getenv of path, it returns the value that is associated with path variable. For example, let's see the value of path and home environment variables. The value of environment variable path is this, and the value of environment variable home is this. Now let's compile this program and get the values of required environment variables. Let's compile env2.c Now we have compiled env2.c and created output file called env2. Let's run env2. Here, out of all the environment variables, we are getting the value of environment variables, path and home. So the environment variables are name and value pairs. Now let's see one more example. In this example, let's see how to set a new environment. Here in this example, we are using the function called as putenv, and here we are creating a new environment variable called as param1 and setting its value to 1024. In this case, we are setting the value inside the main function and we are calling call underscore func1 function, and inside this function we are trying to read the value of param1. Let's compile this and see the output to understand it. We have compiled and created output file called as env3. Now let's run env3. If we see the output, we have created a new environment variable param1 equal to 1024, and we are reading the value of environment variables path, home and param1. We can see that environment variable param1 value is 1024. Now from main function we call the new function, and inside the new function we are trying to get the value of param1 environment variable using getenv, and here we can see that we are getting the same value 1024 both inside the main function as well as in the call underscore func1 function. This means that environment variable is visible for a given process and can be accessible from anywhere inside the process, and it's accessible from different function within the process also. In the next video session, we will begin a new session on memory allocation. Thank you.